Yeah, welcome to the presentation of the paper Deductive Reconstruction of MLT Star for Multi-Level Modeling, held at the Multi-Workshop at Models 2020. My name is Manfred Jeusfeld, and this is joint work with João, Paulo, Victorio, Claudenir, and Bernd. The starting point for working on this paper was that we have at least two proposals in the multi-level modeling community that use a power type pattern to describe how multiple modeling levels can be combined and how to reduce the complexity of modeling by a clever use of the capabilities that you have at the different modeling levels. So the first approach is the multi-level theory by João, Paulo, Victorio, Claudenir, and others, and the second one is deep Tailors, which is based on the Tailors language, and Bernd and myself have worked on this. So we would like to understand the relationship between the two. We do so by attempting to specify the multi-level theory within concept base, which is an implementation of the Tailors knowledge representation language. That language also includes facilities to deal with multiple abstraction levels, but it was not yet capable to support multi-level modeling without certain extensions. So we like to specify the multi-level theory inside Tailors, and that specification will be called MLT-Telos. Yeah, and the final goal will be to use that for checking rather large multi-level modelings for modeling errors, which we did not yet do, but this is the first step in this journey. All the sources and executable examples are on this web page, conceptbase.cc/MLT-Telos. So let's go into the presentation. So the overall result is that MLT star is a superset of what we specify in MLT-Telos. So we could not cover all aspects of MLT star, but important ones. And MLT-Telos itself is a superset of deep Tailors. Well, this is for the impatient, so let's go into some more details. If you look at the papers on MLT star, so I refer you to the paper that you also find on the homepage that was on the previous slide. So if you look at the definition of MLT star, and you see it's defined in first order logic with axioms, and some of the axioms are constraints, and some are definitions defining, for example, predicates with using the equivalence construct. It uses first order semantics, classical first order semantics. That means there's an open world assumptions. So we don't only look at certain interpretations of the models, but all interpretations of the models, of the theory, sorry. So the theory is the combination of all the axioms. Of all these infinitely many models, all these infinitely many models need to satisfy the axioms in order to be models in this multi-level theory. It uses a power type construct, power type predicate, and in addition it also uses categorizations like partitions. It has been implemented, among others, with the Alloy system, which supports open world semantics. In contrast, MLT, Telos, and deep Telos are realized not in first order logic, but with data log with negation. And yeah, that is a logical framework that has only a single interpretation, that is the minimal Herbrand interpretation that is computed by some fixed point operator. Yeah, in data log you have rules, and yeah, some of the rules can be regarded as constraints. We have a closed world semantics. That means things that are not the consequence of the rules and facts, which are special rules without a body. If you cannot derive that, then it's not true. So we have a specific semantic for the negation. Constraints may not be violated, so if you demand that some constraint always has to be true, then adding some facts that would violate them leads to a rejection of these facts. Like with MLT star, power type and categorization are supported, it's fully implemented by concept base. Yeah, and then we have deep Telos. It has rules and constraints. It also has the closed world semantics, same way how to deal with constraints. It supports a power type construct, which is called here in deep Telos most general instance, but it's virtually the same. It's implemented by concept base. So the main difference between deep Telos and MLT Telos is that MLT Telos supports the categorization, as we will see in some example subsequently. Otherwise, they are pretty similar. Good. So a little detour what first order logic and data log mean. So in first order series, you have a set of formulas. You can do some reasoning in the series, so you can prove which formulas are always true when the or a logical consequence of the theory. That means all models that satisfy the theory shall also satisfy the conclusion here. So in first order theory you are more busy with reasoning, and the semantics is all possible interpretation, which are usually infinitely many interpretations. So the focus here is on the theory. In data log, yeah, the theory is called a program. It consists of rules and facts, and formally facts are just rules that have no body, so just a conclusion without any condition. Yeah, you can do some reasoning here, but it's mostly used for finding out which facts are the consequence of this data log program or database that consists of rules and facts. And that is done by computing the unique minimal Herbrand interpretation, which is always finite if you stay within the restrictions of data log with negation. So you can compute this unique minimal Herbrand model, and query answering is to check which facts are in the unique minimal Herbrand interpretation. Then this is the answer to a query. The query definition would be just some rules that define the query. Good. Integrity constraints are special rules that derive inconsistency. So you negate the integrity constraints, and then if you can derive a special predicate inconsistent, then it is inconsistent. Good. Let's relate that to other approaches in multi-level modeling. We have the power type based. So we have two representatives, MLT star and deep telos, and now we will also add the MLT-Telos. And the rest is potency based. So in the power type based approaches, we declare types to be the so-called power types of other types. In potency-based approaches, we assign levels or potencies to classes, attributes, and associations, and that tells or that defines at which abstraction level you can instantiate these attributes and associations. In power type approaches, types or classes are associated via the power type associations, and then the levels are implicit. So there are no level numbers, but you could derive them. So that's also a bit of future work, that we translate a multi-level model represented, for example, in MLT-Telos into one of these potency-based approaches. That will not always be possible, but that's an open research question. All of these approaches somehow are derived from UML. Yeah, so let's see how we represent MLT star. I assume some familiarity with the concept-based system and the underlying language Teilors. If not, then please consult the user manual, where you see the definitions of predicates for instantiation, specialization, and attribution and relations, and also quite a number of axioms that are related to these object-oriented abstractions. So the first step is to define the predefined types of MLT-Telos. The first is entity. That stands for anything in MLT star. So both objects or instances and types. Well, types are more or less a synonym to a class for object-oriented people here. So we define entity to be an instance of a type, because it is a type. It can have instances. Then type itself is also declared. It is an instance of itself because it can have instances such as entity, and we'll see later other instances. And it's also a specialization of entity. So in Telos, specialization is expressed by the ISA construct. That means every instance of the subclass is also an instance of the superclass. So type will also be an instance then of entity, which is what we want. In MLT star, we also have individual, that are those things that are there, but they are not types. So they cannot have instances. So individual is a type because they are individual does have instances. Only the instances of individual don't have instances, and it's also an entity. Those familiar with Telos will note that there is another predefined class individual in Telos, but it has a different meaning. So we use here capital characters to denote the MLT-Telos construct, in contrast to the O-Telos individual, which we don't use here in this paper. Good. So now we define some associations in MLT-Telos. The maybe most important one is power type of. So types can be related to each other by the power type relation. One type can be the power type of some other type. In addition, there is a specializes construct, which is virtually the same as the O-Telos is-a, but for technical reasons we have to declare it here separately. It behaves very much like the O-Telos is-a, but the O-Telos is-a cannot be derived, so we need to derive this specializes predicate or association, and that's why we define it in this way. And then we have proper specializers. We will see later this is derived from specializers. Now there are these headings. They come with a certain meaning. So the for example, antisymmetric and irreflexive, that is defined by integrity constraints and deductive roots. You can find the definitions here in this source code. And that, for example, means a type cannot be a power type of itself. It's also antisymmetric, so if T1 is a power type of T2, then T2 cannot be the power type of T1. It's also one-to-one, so single valued. You can only have one type on this side. If you have one type, then there's at most one type that this type is a power type of, and the other way around. And that is captured by the formulas attached to these categories, single and reverse single. Specializes is reflexive, so very much in difference to the power type, specializes is reflexive. It means every type is a specialization of itself. It is also antisymmetric, and it is transitive. All these categories come with the semantics as deductive roots and integrity constraints in this source code here. So that is declaring the power type and specialization constructs and some of their semantics. So now let's have a look at some axioms here. On the top you see the axioms for MLT star, and on the bottom you see how it is mapped to MLT-Telos in concept base. The first one says if X is a type, X can only be a type if and only if there is no instance Y of there is at least one instance Y of this X. So types have instances, at least one. Individual are the other way around, so an individual X may never have an instance. Yeah, in MLT-Telos, all the variables here must be bound to a class, which is not the case, for example, here. So it's not the same semantics, and on top of this we have here closed word assumption and fixed point semantics. So the formula only approximates what we mean by the axiom in MLT star. So for all X of individual, we may not have any instance of that, so that is the representation for the second formula. And if something is an individual, it may not be a type, which is not mentioned here, but it is added here. In MLT-Telos, we declare objects to be individuals or types, whereas here it is defined. So that's a big difference. When you define a new type in MLT-Telos, then it's initially having no instance. So according to this definition here, it would be an individual. However, during modeling, you first declare something and then you use it. So later, when you use it, you may declare some instances and then it becomes a type. So we do not represent this condition here, but we will have some queries that give you all the types that have at least one instance and all the types that are declared to be types but have no instance yet. Now this is the central axiom for the power type relation in MLT star. So it's defined by an equivalence here. So T1 is a power type if T2 if and only if T1 is a type, and then for all other objects T3, if T3 is an instance of the type T1, the power type, then T3 must be a specialization of T2 and vice versa. So if this subformula here is true and this condition, then this also has to be true. So this can be read in both directions. In MLT-Telos, we only have deductive roots. So if we want to have both directions, then we have to have several deductive roots. So here is the semantics of this power type in MLT-Telos. So whenever you have these three types, and T1 is a power type of T2, and T3 is in T1, so in is the same as has the same intended meaning as the IOF instance of in MLT star. And T3 is not already a subclass of T2, which is the Tailors specialization. So only if we need to, then we derive that T3 specializes T2. The second one says if T1 is a power type of T2 and T3 happens to specialize T2, then T3 must be an instance of T1. So this is the other direction of this equivalence here. Note that we do not derive this predicate, so this is supposed to be declared as a fact, the power type relation. We have no roots for deriving this power type in MLT-Telos. Doesn't say that we can never have that, but not in this implementation. Let's now look at some examples. The most simple example is this one. Person type is the power type of person. Then we declare man to be an instance of person type and woman to be an instance of person type as well. Then by the first rule that we discussed before, there is a specialization link between man and person and woman and person that is derived. Then we can declare some instances of man and woman, and they will be then instances of the appropriate classes. So Bob will also be an instance of person, and Anna will also be an instance of person. So the whole model here is defined by just these facts in MLT-Telos. Note that we have to specifically declare the objects here to be an instance of individual that is not derived as in MLT star. In MLT-Telos we have to find other ways to declare that some object is an individual, and the same with type. So man is a type and person is a type and person type is a type. Good. There's also this instance of declared here. So person is in particular a specialization of itself. So then it must also be an instance of person type. So that is one fact derived from the MLT-Telos roots. Now the other important construct of MLT star is categorization. We only present it here in a short form. So specializations, there are categorizations of types by other types that is used for decomposing them into subsets or subclasses. We have complete and disjoint decomposition, like with sets. This is for the complete categorization. So if that's the case, then it's also also specializes T2, and for the categorization that also specializes T1. Yep. Yeah, the semantics of the categorization is captured here by query classes. Incomplete categorization means that not all entities are covered by the categorization. Complete categorization means all the instances of the subclasses or all the instances of the superclass fall into at least one proper subclass. And the query class here returns you violators. So those classes that have an instance that doesn't fall into a subclass. Disjoint categorization is covered by this query to find entities that are in both in two different types. The type that is returned here in the answer, and the type that is returned here in this answer variable small caps type. So the queries returned are violators. Let's see an example here. So person is an incomplete categorization because there is this instance here, data, that is not falling into these two subclasses. So data is not an instance of man or woman. So this is an example of incomplete categorization. And non-disjointness is because Anna here is declared to be both an instance of man and woman, so this is not disjoint. This is depending on this partitions construct that we use here. Partitions is subsuming disjointness and completeness. So we activate these the semantics of this by just using partitions. When we graphically visualize that, then we can see that person is a violator and man. We can also use the textual answer to the query, and then we see a little bit more information. So person is an example of an incomplete categorization, superclass person, because there is an entity data, and man is a non-disjoint categorization, or is a violator of disjoint categorization, because there is an entity Anna, and the type to look at is woman. So Anna is also an instance of woman and man. So that's the how to read the answer to this query. Yeah, so coming to the result, deep Tailors versus MLT-Telos. The full paper lists all the deductive rules to map a deep Tailors model into an MLT-Telos model, and that means that practically all models that are written in deep Tailors can also be read as an MLT-Telos model, and that goes so far that we don't even have to change anything. We only have to add some more mapping rules, the deductive rules to map, and then it also works as an MLT Telos model. In particular, we map the most general instance construct of deep Telos into the power type construct of MLT Telos. Deep Telos does not have the categorization construct, so you could say Deep Telos is a subset of MLT Telos. Yeah, the original papers of MLT star do not specifically talk about how to handle attributes and relations. It may be an implicit consequence of the axioms, but there is no notion of attributes and relations mentioned in the axioms of MLT star. In contrast, Deep Telos does handle that, and consequently MLT Telos can take over this aspect of Deep Telos. So having some definition of how to deal with attributes and relations in MLT Telos. Last year, Deep Telos passed the Multi-19 challenge, so most likely MLT Telos will do as well. Yeah, some limitations. We did not yet test large models, so it could be that large models pose a challenge to the implementation, that it takes too long to load or analyze them. Yeah, there is also a technical limitation that O-Telos uses its own specialization construct. This is not completely integrated with the specializers construct, though their intended meaning is the same. And that leads to a few problems when specializing attributes or relations. So in a subclass you can specialize an attribute of the superclass, and that is supported by O-Telos, but it's not fully supported by MLT Telos if you use the specializers construct. But that's a technical constraint that can be overcome by adding some code to the implementation of concept base. The more fundamental limitation is that MLT Telos uses a minimal Herbrand interpretation. So MLT Telos cannot derive power type relations from a given multi-level model, whereas MLT star can do that. MLT star doesn't really favor the position of a certain predicate. So if you have a logical equivalence, you can transform, for example, an implication, and move predicates from the conclusion side to the condition side by negating that. In data lock, that is not the case. The position of a predicate in the condition or the conclusion makes a big difference. If it's in the conclusion on the conclusion side of the deductive rule, then we can derive facts for this predicate. Otherwise, we would have to have a rule for that. Yeah, we only have a very simple implementation for the notion of what is a basic class and an ordered class and an ordered type and an unordered type in MLT-Telos. Yeah, so that's about it. So the benefits of MLT-Telos, it is rather short. The source code fits on one page. It provides the potential for an efficient implementation. Efficiency because the data log engine as such is efficient, though you can always have problems if you have too many rules or too many rules of a certain structure in data log. We have a small number of query classes, like for this non-disjoint categorization to check correctness. This can be extended. You can also add query classes that qualify a multi-level model. So not just finding errors, but also undesired models where the maybe the number of subclass definitions is excessive or redundant. Yeah, all the sources and the examples are published under Creative Commons by share alike, so attribution share alike. You can play with the examples by going to this page and then download the concept-based system, and then you can directly work with the examples. Thank you, that's all, and questions are welcome via appropriate channels.